All right, this chapter involves motion along a straight line. Let's first begin with the key equations, and you'll see that it has the very familiar x for position or displacement, v for velocity, and a for acceleration. What we're going to do is discuss each one of these in groups as we go through the sections within the chapter. Now we can first look at a case where you have a person moving to the right, going a distance of 0.5 kilometers, then 0.5 kilometers to the left, then 1 kilometer to the right, and then 1.75 back over to the left. Now, some of the questions that you can ask about this person moving around is what is their total displacement? And the way that you do that is you begin to add or subtract these distances because these displacements are vector quantities. So we have a minus 0.5 and a minus 1.75, giving a total displacement of, to the left, 0.75 kilometers. The other question you can ask is what is the magnitude of the final displacement? Now that simply is just taking the absolute value of the answer we got for part A. And so the answer is 0.75 kilometers. Another question you can ask is what is the average velocity? And so here we're going to refer to the equations to the upper right hand side where we're dealing with the case of taking basically the final minus the initial for the total displacement over the total time. So in that case, what we're going to get is we have the negative 0.75 kilometers divided by the sums of the times. Now you'll notice that I have 9 minutes to the right, 9 minutes to the left, and then the person takes 15 minutes to go the 1 kilometers and 25 minutes to return back the other direction, 1.75. So 9 plus 9 plus 20 plus 15 plus 25. And then also notice that I'm converting from minutes over to hours so that my answers come out, comes out in kilometers per hour. Then looking at part D, it says what is the total distance traveled? And in this case, what you're going to do is basically take the absolute values of all of those displacements so you can find the total distance that they traveled. So this might be what would be displayed on, say, an iPhone app that's measuring your distance that you walk, or maybe converting the number of steps into kilometers. If we were to make a graph of this person's position versus time, what you'll find out is that, first of all, starting at time equals 0, we're at position 0. You'll notice we moved forward in a positive direction, 0.5 back to 0 again, or back to home. And then we're going a distance of 1 kilometer here, and so we end up at a distance after that length of time right here of negative 0.75 kilometers. In section 3.2, we're talking about instantaneous velocity and instantaneous speed. We have a plot of position versus time. Now this is a different scenario than the one we talked about previously. In this case, the object moves a distance of 0.5 meters, stays there for a while, and then comes back to the original position. What we can do is use a graph of position versus time to figure out what the velocity is versus time, simply by taking the total distance traveled over elapsed time for each of the sections. So let's look at this first section in which we have a positive slope on the position. If we look at the total distance traveled, we see that it's 0.5 and the total time is 0.5 seconds. So 0.5 meters over 0.5 seconds gives you 1 meter per second. And then if we look at the second segment right here, we find that we're not moving any distance. So the numerator up here is 0. So that means that the velocity is 0 during that length of time. The slope of this is 0. And so that's why we get the 0 right here. The slope of this turns out to be 1. That's why we get 1 here. Then looking at this last segment, what we find out is we take the final position, which is 0, and then we look at the initial position, which is 0.5. So we say 0 minus 0.5. And then we divide that by the length of time that it goes from here to here. And that looks like to be 1 second here, and then 2 seconds there. So the duration is 1 second. So the change in position is, if we look final minus initial, it's 0 minus 0.5. That gives you a negative 0.5 meters divided by the 1 second interval. And that's why we get a negative 0.5 meters per second on this one. So anytime you have a plot of position versus time, you can take the slope at any one instant and figure out what that instantaneous speed is. So here's a positive slope, so we get a positive velocity at a quarter of a second. Then at half a second, we have a zero slope, so our instantaneous speed is 0. And then down here at 1 second, we have a negative slope. So in this case, at 1 second, we have a negative velocity. That's the, that's the instantaneous velocity of, let's say, -5 meters per second. If you take the absolute value of this graph, then you're able to get the speed. It's not so common that you represent this graph here, but you can basically see these negative things went positive once we took the absolute value. In section 3.2, we see a definition of instantaneous velocity that deals with a derivative. In fact, you may see a derivative in this course before you see it in calculus. The way that we read this is velocity is equal to the derivative of the position with respect to time. Or another way to read this is the velocity is d by dt of the position. Now what we can do is look at a very simple example of a polynomial and looking at the derivative here. So equation 3.7 is showing you the generic form of taking a derivative with respect to time of a polynomial where a is a constant, n is a constant, and t is time. So to show you some examples of that, what you can do is say, what is the derivative of t squared with respect to time? And all you got to do is take the 2 and pull it down and then subtract 1 from it. You see it right here, right? So you pull the n down over here and then it's n minus 1. Another example would be looking at t cubed. We pull the 3 down, n minus 1 is, in this case, 3 minus 1, which is 2. Looking at another example, 4, you pull the 4 down and you get 3. So polynomials are not that difficult to find the derivative of just because it's kind of a recipe here. Notice now that if I introduce a constant of, in this case, 5, that I simply leave it out there in front, I have to pull the 2 down, so 2 times 5 is 10. 2 minus 1 is 1, so I just basically get t. A pretty rare one that you see in solving physics problems is just d by dt of t. And you can see, just use your imagination here and see why it's equal to 1. Basically, it's saying, what is the slope of t? And it turns out to be 1. Now let's look at an example of a specific position as a function of time. So here we have 3.0 t plus 0.5 t cubed meters. So it's understood that there's basically no units within this left spot right here, and that the units that comes out of this over here is meters. So moving on, what we can do is remember that velocity is basically, as we can see here to the upper right, the instantaneous velocity is d by dt of x, which is a function of time. I've written it a little bit differently over here. You can see that I've written it in one line rather than a ratio one over the other, but the meaning is the same. So in this case, what we can do is take the derivative of that first equation and see that d by dt is just 1, so we just leave this as 3. And then we take the 3, multiply it by the 0.5 and get 1.5, and then reduce the t cubed to t squared, and then remembering that velocity is measured in meters per second. One of the things we learned in section 3.3 is that number 1, acceleration is a vector. Number 2, it's the change in velocity over time. And number 3, if you take the derivative of velocity with respect to time, you can find the instantaneous acceleration. So in this particular example, what you see is that initially the object is moving to the right, and finally the object is moving to the left. And so the only way that can happen is if it's decelerating. In other words, that the acceleration has to be in the opposite direction to the initial velocity. If we look at an example in which we can find the instantaneous acceleration from velocity, we simply refer back to this equation up here to the right that says the derivative of velocity with respect to time should give us the acceleration. So moving forward with that, we can see that a is dv dt, and then if we look at the first one, we get 20 and then dt is just 1. And then we look at the 10, and so the way we get the 10 is that the 2 comes down, giving you 2. 2 times 5, giving you 10. And then you say n minus 1 for this, and so we just get t. Also realize that acceleration has the units of meters per second. So in section 3.4, we're primarily dealing with cases of constant acceleration, and so you get these very familiar kinematics equations. V is equal to V naught plus AT. X is equal to X naught plus V naught T plus 1/2 AT squared. These are only true if acceleration is constant. This is the final velocity, and this is the final position. So looking at this vehicle over here to the left-hand side, let's assume that it starts at the origin at rest, and you accelerate at a constant acceleration positive toward the right, 26 meters per second square. We want to know how far did it go and what was its final velocity if the length of time for this acceleration was, let's say, 5.56 seconds. So we pull one of these kinematics equations down from over here to find out the position. And if we feed in what the knowns are, you see that it starts at the origin, so that's why that's 0. It starts from rest. I got the time right here, how long it was accelerating. And then also have the time down here, 5.6 seconds square. Here is my acceleration. It's positive, and I got the 0.5 because of the half here. You work all this out in your calculator with 3 significant figures, 402 meters. Now what you can also do is figure out what the velocity is, and here we're pulling from the other kinematics equation, velocity from acceleration, assuming acceleration is a constant. We put all of our values in here. It starts at rest, accelerates at this acceleration for 5.56 seconds. You notice the units cancel out, at least as far as the seconds go, and you're left with meters per second, in this case 145 meters per second. What you could do is, if you know these two things, the distance traveled and the final velocity, you can actually plug them into this last equation I have down here to figure out what the acceleration is. So you can imagine a problem in which you're not known, you don't know what the acceleration is, but suppose that you're given how far did it go and what was its final speed, then you can calculate the accelerations. Here I've simply solved for A, and so I get V squared minus V naught divided by 2 times X minus X naught. So if I plugged in 402 down for here, put a 0 here, I put in 145 for this and 0 here, I'm going to find the acceleration, and it should be equal to 26 meters per second square. Now in section 3.5 is talking about free fall, and when you have objects falling in air, strictly speaking, it's not free fall. If you have an object such as a hammer and a feather dropping in a vacuum, then they're going to hit the ground at the same time if you drop them from exactly the same height. This was repeated, or this experiment was performed on the moon during one of the Apollo missions. So in this section 3.5 on free fall, you'll see that our familiar kinematics equations have been modified so that the acceleration is negative g in each one of these equations. That's really the only modification. And notice that the lowercase g is equal to 9.81 meters per second square, or 32.2 feet per second square. Notice that this is not a negative number. These are positive numbers. It's the acceleration that's negative, as you'll see if we say a sub y, or the acceleration in the y direction, is negative. So in this course, we will always say that g is a positive number, although the acceleration is negative if, for example, we choose up to be the positive direction. Let's consider a scenario in which a baseball player pops the ball straight up in the air, and we're going to call this position you see right here y is equal to 0. So that's the origin. And then sometime later, it comes back down in the same spot right here where y is equal to 0, and it lands in the catcher's glove, and this happens 5 seconds later. So what kind of questions can we ask about this? What might we see in our homework, for example, or on an exam? Some questions you can ask about this from a physics point of view is, what was the speed at which it left the bat? So just at the moment it left the edge of the bat, what was the speed going upward for this scenario if it takes 5 seconds to land in the glove? The other question is, how high did it go? So these are calculations that we can perform simply knowing what the time is. So let's consider the first question. What was the speed at which the ball left the bat? And so what we can do is begin by pulling out one of our kinematics equations that have been modified for the acceleration due to gravity. In this case, the final velocity is equal to the initial velocity minus gt. Now, if you proceed through that and you assume that at the top of its trajectory, we're going to call that t-top, going all the way up here, that's t-top, and then coming back down here. You can see that since the total time is 5 seconds, then the time it takes for the ball to get to the top of its trajectory is going to be 2.5 seconds. So that's what t-top is equal to. At the top of its trajectory, the velocity is equal to 0. It comes momentarily to rest. So it has a positive velocity here and a negative velocity here and a 0 velocity up here. But the entire path has an acceleration of minus g. So minus g here, minus g here, minus g here for acceleration, even though we have a positive velocity, 0 velocity, and a negative velocity here. So plugging in the velocity at the top of 0, we can figure out what our initial velocity is simply by knowing the acceleration due to gravity, and then knowing that this t-top is 0.25 seconds. So we're able to find out that the velocity is simply equal to 9.81 meters per second squared times 2.5 seconds, or 24.5 meters per second. So that's one of the questions we can ask is, what is the speed at which it leaves the bat? So now let's try to answer the question, how high did it go, using the height of free fall. Y is equal to y naught plus v naught t plus 1/2 a t squared, or in this case, the a is, negative g, so we have that modification. So when we look at our scenario and see that it started at 0 and ends at 0, we can put a 0 here, a 0 here. And let's assume we don't know what the velocity was from the previous slide. And we have the rest of this, listing our unknowns. But we really know some of these, so let's plug them in here. Oh wait, before we do that, let's move, v naught t to the left-hand side. That gets rid of one of the minus signs, or the minus sign here. We cancel out one of the t's, so we're left with v is equal to 1/2 gt squared. And you begin to realize that when you plug in these numbers, here's the value of g and here's the 5 seconds from here over to there, you're not answering the question. You're getting that the velocity is the same that we got before, 24.5 meters per second, but that's not answering the question, how high did it go? It would seem like this equation should tell us that. And it does if we, again, consider the path halfway. So in other words, look at the time and the velocity at the top of its trajectory. So let's rework that this time by saying, let's consider the time not to be 5 seconds like we did up here, but instead 2.5 seconds. And so at the top of its trajectory, it's going to be at rest if it goes straight up. And so it'll be at rest just for a moment at the very top. Plugging those values in, now we're going to say that y is the height that it goes. And initially it's at the origin. We know this one right here from the previous two solutions we worked on, 24.5. T-top is 2.5 seconds. Plugging all of that in here, 24.5, 2.5, minus 1/2, 9.8 meters per second squared. And don't forget the square out here on the end. And then we get the total height is 30.6 meters. So sometimes you have to be careful about, in projectile motion, about whether you should look at the total time of flight, or at least or instead consider the case where you're talking about half of the projectile motion. So as you can see, the key equations pretty much summarize chapter 3 very well. And to me, it's not about memorizing the equations. It's more about understanding what each of the variables mean and how to use the equations. That's what makes you a powerful problem solver. You're going to naturally begin to remember these equations over time as you begin to solve more problems. That's going to happen, but it's more about understanding how to use them in physics. And that was Chapter 3, Motion Along a Straight Line.